Welcome back to the next video, everybody. Today we're going to give a cohomological interpretation of Zariski tangent modules. So the setup is this. We'll fix a profinite group pi satisfying p finiteness. We'll let rho bar from pi to gln of k be a continuous residual representation, where k is a finite field of characteristic p. We'll let lambda be a coefficient ring with residue field k. We'll also fix a specific homomorphism rho from pi to gln of a, where a is a coefficient lambda algebra. And we're going to consider the deformation problem relative to rho, which, as we recall, means we're going to look at the functor d sub rho from c hat lambda of a to sets. More precisely, we're going to consider its Zariski tangent a module, td rho a, which remember is d rho of the ring of dual numbers a bracket epsilon, which we'll write as t sub rho. That's our Zariski tangent space. Okay, we would like a cohomological interpretation of this entire setup. It'll be very helpful for us. Okay, so let's let V be the free rank n a module V equals a to the n, endowed with the a linear pi action given by the composition of rho with the natural action of gln of a on V that we have. Okay, so we'll let end a of V denote the free a module of rank n squared consisting of a linear endomorphisms of V. The action of pi on V induces an action of pi on end A of V, as usual. And this is the adjoint action. Here's the formula if you don't know this. The action is that G dot E of V is rho of G times E of rho of G inverse of V for G in pi, E in end A of V, and V in big V. Okay, so here's a proposition for you. Here's our cohomological interpretation. Proposition 15, there's a natural isomorphism of A modules between the tangent space T rho and H1 of pi on end A of V. And so using this, we can close up a link in our chain, which is we can finally state weak and strong finiteness, which, as you recall last video, were used to prove our main results of the chapter on existence of universal deformation rings using Schlesinger's criteria. So proposition 16, weak finiteness, it says let A be an Artinian coefficient lambda algebra. Then T rho is a finite A module. And this is proven in CSS page 286 using proposition 15 and P finiteness. Corollary, if rho bar is absolutely irreducible with a universal deformation ring R, then as A modules, the A maps from omega of R over A, so my space of differentials, completed tensor product over R with A to A, that's isomorphic to T rho. And that's isomorphic to H1 of pi Mn of A, where Mn of A is n by n matrices over A. Okay, and so in particular, if you set A equals K and rho equals my residual representation, rho bar, my tangent space T sub R is isomorphic to K map. So basically I get tangent space is isomorphic to H1 of pi Mnk. Because remember, K maps from Mr mod PMR squared to K. Mr mod PMR squared is my cotangent space. And so the K maps out of it to K would be my tangent space, right? So the proof of this is basically, it boils down to propositions 8 and 15. All right, there's really nothing to prove. We've kind of done all the work. And then there's a strong finiteness condition used to prove strong representability from last video. But as I said last video, we don't really need that result, but let's go through it anyway. It says let A be a coefficient lambda algebra now. Now you don't need the word Artinian here. Then T rho, this tangent space is still a finite A module. So the proof of this is in Cornell, Silverman, Stevens, page 286, and it uses Schlesinger's theorem. You can also see Mazur's original deformation theory paper for a proof of this. So as a corollary, let A be a coefficient ring with finite residue field of characteristic P. Let pi be a profinite group satisfying P finiteness. Let M be a free A module of finite rank with a continuous A linear pi action. And let H1 pi M denote the continuous one-dimensional cohomology of pi with coefficients in the A bracket pi module M. Suppose H1 of pi M is given its natural A module structure, okay? Then H1 pi M is actually finite type as an A module, okay? So the proof of this is basically a combination of the above. If you want details, it's CSS page 287, okay? So we get some finiteness of certain cohomology groups here, which will be useful later on, okay? But again, like, the main point of this video is to fill in gaps for the big results on deformation problems that we stated last video. So we'll continue to look into this stuff next video. I'll see you then, and thanks for watching.